Now consider a point mass, let's say capital M. Okay. And consider a position at a certain distance from it. This position, you can call it A. Now, if another mass takes this position, right? If some small m comes to that place, it will experience a force from capital M. Okay. Now, instead of this mass small m, if some other mass comes here, then that other mass also will experience a force. Whichever mass comes to that position or takes that position experiences a force from capital M. So we can think of it like this. We can say that capital M has already influenced that position in some manner. Okay, it is already showing some effect at that place, and whichever mass comes to that place is feeling the force. Okay, that effect which capital M has created at A, at that position A, is something we call as gravitational field. Okay, whether this other mass is present or not, that point in space is already influenced by capital M. Okay, that influence created by capital M there is what we call as gravitational field of that mass capital M. Okay, so not just this point mass, every mass in the universe creates a gravitational field. Okay, any particle you take around you, that particle has its influence in the space surrounding it. Up to what distance? Up to infinite distance it has influence. Okay, so mass influences the space around it. That influence which a mass has on the space around it is what we call as its gravitational field. Fine, it's a proper physical quantity. There's a definition, unit, dimensions and all. We'll discuss that in detail now. So consider some position in space. Let's say this one. Now, the masses surrounding this position would have influenced this space already. Okay, that will always be there. You can't say no to that. Okay. Then to find out the gravitational field at this position, what we do is we assume there is a mass present here. Okay, it may actually be there, it may not be there also. It need not be there also. You imagine it is there. Okay. Now this point mass is placed there to check how much influence the other masses have created. Okay. Other masses could be here, here, anywhere in space. What is the gravitational field at that position is what we want to check. Means what influence the other masses have created there is what we want to check. So to check that, we keep a small point mass there. Okay. It's called a point test mass. We want to test how much influence the other masses have created. Okay. Now this mass will experience some force. Let's say it experiences a force this way. Gravitational force. Now who exerts this gravitational force on this particle? Other particles. Okay. Other masses. Then the gravitational force experienced per unit test mass is what you call as the gravitational field. That is the influence that has already been created at that position. Okay, and it's a vector equation. Gravitational field denoted by the symbol E. Okay, by definition is gravitational force per unit mass placed at a position. Okay, we'll derive gravitational field produced by different geometries. You'll understand better, but this is the basic definition. Gravitational force per unit mass. Okay, one of you quickly tell me what the SI unit of gravitational field will be. It's also called field strength or field intensity. Okay, basically how strong the influence is. What will the SI unit be?
Sir, is it newtons per kilogram?
Newton per kg, correct. Okay. Now, gravitational field is gravitational force per unit mass. you can write this equation in reverse also. You can say that the gravitational force, okay, acting on a point mass is the gravitational field multiplied with the mass itself. Okay, so if you know the field at a particular position, field means the influence that is already present at that position, multiplied with whatever mass comes to that position, you can tell how much force it experiences. Okay, let's solve the problems based on this, based on the definition first. Note down this formula, all of you. By definition, gravitational field E is gravitational force per unit mass. And if you want force, it is field multiplied with mass. Let's say a point mass of 4 kg placed at a certain position experiences a gravitational force of, okay, this is a direct question. You can answer this straight away. 30 newtons. Okay. How much is the gravitational field at that position? You don't even have to use pen and paper to solve this. Answer directly. Give your answers in chat. Basic definition based question. The force experienced per unit mass is what you call as gravitational field. So 7.5 Newton per kg. Next. Suppose there exists a gravitational field given by this equation. Okay. Now you can see that the field expression depends on the x coordinate and y coordinate. Means from place to place the field changes. Depending on xy coordinates of that position, the field changes. So we call this as a non-uniform field. Any quantity which changes from point to point is called or is said to be non-uniform. So this is a non-uniform gravitational field. Now using field, what can you calculate? If you know the gravitational field and how much mass is present in that field, you can tell how much force it experiences. Okay. So try this now. Suppose there is a mass of point mass only. Let's say there is a point mass of 3 kg at the coordinates 2. Okay, let's take 2, 1. Calculate the gravitational force it experiences, and due to that force, how much is the acceleration? Solve this quickly. Let's see. Rishi, unmute yourself. No response. Okay, Vanilla, unmute. How do you
Yes.
calculate gravitational force on a point mass from field?
So E into M.
Field multiplied with the mass. Okay. Now the mass is located at 2, 1. So in place of x, you are supposed to substitute 2, and in place of y, you'll substitute 1. So the field there becomes 2 into 2 I cap plus 3 into 1 j cap. That's the field. It's in SI units, and you multiply that with mass. So 4 I cap plus 3 j cap multiplied with 3. Effectively, it is 12 I cap plus 9 j cap newtons. This is the force. And if you take its magnitude, it will be 15 newtons. Root of 12 square plus 9 square. Okay. That's all. Gravitational field multiplied with the mass that is present in that field. That mass is located exactly at 2, 1. So at that position, you find out the field first. Multiply that with the mass. Next, acceleration. Acceleration is nothing but force per unit mass. We'll assume, actually, acceleration is net force per unit mass. We'll assume this is the only force acting on that mass. Okay, otherwise, how can you tell acceleration? Now, the force here is 12 I cap plus 9 j cap divided by the mass is 3 kg. So acceleration becomes 4 I cap plus 3 j cap, effectively 5 meters per second square. And notice one more thing. We got the acceleration as 4i cap plus 3j cap. This is acceleration due to gravitational force. And it is the same as the gravitational field. So basically, gravitational field is acceleration due to gravity itself. Okay, you'll understand that better as we solve more and more problems. But for now, what you need to remember is you can use gravitational field to find out how much force a mass experiences. Is this clear to all of you? Any doubts in this? Okay. Let's try another problem. Assume there is a gravitational field of some 4x I cap. So this is also a non-uniform field. Based on x coordinate, the field strength changes. Direction of the field is I cap, x direction. Okay. Let's say there is a rod of mass 2 kg. The rod is not a particle. It won't be at a single point. Okay. Let's say there's a rod of mass 2 kg lying on the x-axis between x is equal to 0 and say x is equal to 2 meters. Okay. So there is a gravitational field in space, and in that field, this rod is lying. Now, in a gravitational field, if any mass is present, it will experience a force. Calculate the force acting on the rod. Calculate gravitational force on the rod. Okay, let me help you visualize the situation. Assume this is the x-axis. A rod lies on this x-axis between the positions x is equal to 0 and x is equal to 2. Okay. There is a gravitational field 4x I cap. The field depends on the x coordinate. So at the left end of the rod, the x coordinate is 0. That means the field is also 0. Okay. The left end of the rod won't experience any force. Let it be. But you take any other point of the rod, somewhere here, where x coordinate is maybe 0.3 or something like that, then there is a gravitational field present there. And if field is present, that element of the rod experiences a force. Okay. So you should find out what force or how much force each element experiences and add that to get the total force on the rod. Okay. Start solving. Gravitational field is given. All quantities are in SI units. Mass is given and dimensions are given. Fine. See, we know the mass of the rod and we know where it is lying. It's not a point mass. Okay. So if you want to use F is equal to, the force is equal to gravitational field multiplied with the mass, it gets a little complicated here because the field is not the same for the entire 2 kg. Okay, because this is a field which varies from point to point, non-uniform field. Had the field been same everywhere, you could have applied F is equal to EM and gotten the answer directly. So what you have to do, since field varies from point to point, you have no other choice. You have to treat the rod as a collection of particles. Okay. So consider one element of the rod. Assume its mass is dm. Okay, the same routine procedure that we do. Let's say it is present at some random coordinate x and assume its length is dx. Why should we do all this? Because the gravitational field depends on the coordinate. And unless you know how much field is present at that position, you can't tell how much force this element experiences. Okay, so field depends on the coordinates. So let's say the coordinate is x, the mass is m. Then this element will experience a small amount of force because the mass is small. So you can write df, the small force experienced by this element, as dm, the small mass of this element, multiplied with the field at that position. So that becomes dm multiplied with, what is the expression for field given in the question? 4x I cap. So that's the force experienced by this one element. And in which direction will it be? Whatever is the direction of the field, same will be the direction of the force. So this element, this yellow element that we have considered, experiences a small force in this direction. Similarly, every element will experience a force due to this field. Wherever the field is non-zero, the mass experiences a force. And we want the total force on the rod, so we'll have to integrate this. And we discussed this in the last class also. Force is a vector quantity. When integrating forces, it's like summing up vectors. And while summing up vectors, you need to see first if all vectors are in the same direction or not. Now you consider another element of this rod, maybe somewhere here. There also, the gravitational field will be in the positive x direction because field expression is 4x I cap. Where x coordinate is positive, the field will be positive. And if field is positive, the force will be in the positive x direction. So that element also experiences force in the same direction. All elements are going to experience force in the same direction. So you don't have to bother about or worry about taking components of this force and all. You can directly integrate df to get the total force F on this rod. Therefore, the total force on the rod becomes integral of small forces. That becomes integral 4x I cap dm. Now you can't integrate 4x with respect to m. You'll have to express dm in terms of dx. Aishwarya, tell me how to write dm in terms of dx in case of a rod.
Lambda dx.
Correct. dm is equal to lambda dx because this is a linear mass distribution, where lambda is total mass by total length, and we know that already. So we'll put the constants outside the integral. 4 is constant, lambda is constant, I cap is also constant. I cap just gives you the direction of the force, let it be. What are you left with? X dx. Now from where to where do you have to integrate x? In order to cover the entire rod, x should vary from 0 to 2. Okay. Integral x dx is x square by 2. Then you substitute limit 0 to 2. 2 square by 2 is 2 itself, and 0 square by 2 is 0. So this integral becomes 2. Therefore, the answer is 8 lambda I cap. Now, what is lambda? Total mass by total length. So 8 into total mass of the rod is given as 2 kg. And the rod lies between x is equal to 0 and x is equal to 2. That means the length of the rod is 2 meters. So lambda is 1 actually. Total mass by total length. I cap. The answer is 8 newtons. Okay. Go through this once again. Ask if you have any questions. I'll give you 1 minute. Right. So if you know the gravitational field in a certain region of space, you can find out or you can calculate how much force an object there experiences. Now, who creates this gravitational field? Mass only has to create gravitational field. No, we talked about this already. Every mass has some influence on the space around it. That influence is what we call gravitational field. Okay. So in the presence of field, we now know how to calculate forces. Let us now calculate how much field is created by a certain amount of mass. So first case, the gravitational field of a point mass. We'll first find out how much influence, how much gravitational field a point mass can create anywhere in space. Using that, we can tell how much influence extended objects can create. Okay. So suppose there's a point mass present here. Let the mass be capital M. We want to find out how much influence it has at a certain distance x from itself. Okay. So the question here is to derive the gravitational field that it produces here. Now, by definition, gravitational field is the gravitational force acting per unit mass on a test mass that is placed at that position. So what I want you all to do is imagine a small particle present here, small m. Okay. Write the expression for force experienced by small m or force acting on small m. Write the expression for it. Then you divide the force by the mass small m itself. You will get the expression for gravitational field. Okay, do this all of you. I'll give you 1 minute. Rishi, tell me how much force does the particle small m experience? How much gravitational force does it experience?
Sir,
What's the formula we know for gravitational force between point masses? Come on, basic gravitational force formula.
G m1 m2 by r square.
So here it will be G capital M small m divided by x square. That is the force it experiences. Then you divide that by small m itself. Then the field becomes G capital M by x square. Okay. So G capital M by x square is the gravitational field strength of capital M at that position. See, we assumed small m to be present there only to calculate this field. So this small m is called a test mass. Small m is not the one which created the field. Capital M created the field. Small m experienced the force due to that field. Okay. And field is force per unit mass. Force is a vector quantity. Mass is scalar. Mass is always a positive scalar. Okay. Mass can never be negative. So if you divide a vector by a positive scalar, the result will still be a vector which is in the same direction as the force. Okay. So this is also very important. Gravitational field and gravitational force will always be in the same direction. So what have we found out here? We found that a mass capital M at a certain distance from it, okay, at a certain distance x from it, creates a gravitational field, means it influences that space. By what strength? It creates a gravitational field of G M divided by x square at that position. So if some mass comes to that position, due to the presence of this field, that mass will experience a force. Okay, like this, every mass in the universe influences the space around it, and how strongly it influences depends on these factors: how strong the mass is and how far the point is from the mass. Okay, this is the gravitational field strength of a point mass at a distance x from it. And what is the direction of the gravitational field? It is towards the point mass itself. Okay. We can even draw a graph of this. A graph indicating how the strength of the gravitational field varies with distance from the mass. Okay, listen to this carefully, all of you. These graphs are very important. I mean, you should know how to draw a graph based on a formula. On the y-axis, we denote the field strength, only the magnitude. We are not bothered about direction for now. On the x-axis, we denote the distance. Okay, distance of the point, distance from the point mass. Now we just derived that the gravitational field of a point mass is given by G capital M divided by x square. G is universal constant, gravitational constant. M is the point mass. That is also a fixed value. Distance varies from point to point, and based on that, the gravitational field strength varies. Now, if distance tends to 0, it's like denominator tending to 0. Numerator is positive. Denominator tends to 0 means the field strength tends to infinity. So if you go very close to a point mass, the field strength tends to infinity. Okay. And x square is in the denominator. As x square increases, as the denominator increases, the whole thing will decrease. The field or the entire fraction, if you see, its value will decrease. So when you are very close to a point mass, the field strength will be very strong. And as you go away from it, the field strength decreases and decreases. And when distance from the point mass tends to infinity, then the field will tend to 0. The whole thing will tend to 0. Okay. So this is how it varies. When distance tends to 0, the magnitude tends to infinity. You can't show that on the graph. So up to a certain distance, we draw a dotted graph. After that, we show it decreasing like this. It's not that we are drawing a random graph. If you plot values, okay, for this function, it's like y is equal to gm is a constant divided by x square. For this function, if you actually take some x coordinates and get y coordinates, this will be the shape of the graph. Okay. So what have we just derived? We derived how much gravitational field a point mass creates at a certain distance from it. Now, what if there are multiple point masses? They will all create fields. Then you will be required to find out the net gravitational field produced at a certain point. Let us work on that. So remember the idea. Each point mass creates a field of gm by x square towards itself. And if there are multiple point masses, multiple fields will be created at the same place. And you have to find out the net field by treating individual fields as vectors. Okay. It's a vector quantity. You have to treat it as a vector. Okay, solve this problem. Suppose there are 2 point masses lying on a straight line. Let's take one mass as 2m, the other mass as m. And okay, the distance between them, let it be a. Calculate the net field produced by these two masses at this position. Where is that? That position is at another distance a, at a further distance a from small m. Okay, find out the net, calculate the net gravitational field produced at that position by these 2 point masses. Okay, do this quickly, all of you. I'll give you 2 minutes. Okay, Rishi, you tell me. Let's name these particles as A and B. How much gravitational field does A create at that position? No response. Okay, Aishwarya, first tell me the formula.
Sir,
Continue.
is it G2M m by a square?
Okay. First, the formula for gravitational field produced by a point mass is Gm by square of the distance from the point mass. Okay. Field won't have two m's in it. There will be only one mass. Okay. So the mass 2m will create one field there. Okay. And it will create a field towards itself. Gravitational field is always an attractive field. The field created by the mass 2m, let's call it as E1. That will be G 2m divided by the distance from 2m to that point is 2a, and you have to square it. So 2gm by 4a square, that effectively becomes gm by 2a square. That's the field produced by the first particle, A. Next, the particle B, it will also produce a field there towards itself. We don't know how much field it produces, so I'm drawing a vector of a random length. Towards itself means that will also be to the right. Okay, you have to visualize fields along with the directions. Okay. Then the gravitational field produced by the particle B, we're calling it as E2, will be G, the mass is m, divided by the distance is a, and you square it, gm by a square. And both the fields are in the same direction. Therefore, the net gravitational field, if vectors are in the same direction, you can directly add their magnitudes. Gm by 2a square plus gm by a square becomes 3 gm by 2a square. And direction is to the left, so you can write minus I cap. You can express only the magnitude or along with the direction. Is this clear to all of you? Any doubts in this? Okay, let's move on to the next question. Suppose there are 2 point masses again, one on the positive y-axis and one on the negative y-axis. Both of them are at a distance d from the origin. Find out the net gravitational field. Okay, the masses are m and m. find out or calculate the net gravitational field produced by this combination at a distance x on the x-axis. So I want you to derive the net gravitational field at this position. Okay, just the magnitude. Do this carefully, all of you. Remember, each point mass produces a field there. So you have to calculate what is the field produced by each one of them first, how much, and then add the fields as vectors. If they are in the same direction, you can directly add them as numbers. But if they are in different directions, you will have to use a resultant formula. Okay, or maybe take their components and add components separately. One of those ideas you'll have to use. Try. Let's discuss. I didn't get any answer so far. As I said, both point masses create the field there. We have to find out the net field. When you'll unmute yourself. First, what is the formula for gravitational field created by a point mass at a certain distance from it?
So gm by x square.
G multiplied with the mass divided by the square of distance from the mass. Okay. Now here, just to avoid confusion, let's call this distance on the x-axis as x naught. Okay. To find out the individual fields, to calculate individual fields, we need to know what is the distance from the particle to that position where you are asked to calculate the field. And that distance becomes root of d square plus x naught square. For the other particle also, it's the same distance. There is a symmetry in this situation. This will also be root of d square plus x naught square. Okay, so we get the distance from each particle to that position. So we can now express the fields produced by each one of them. Okay, directly substitute in this formula. Let's call the masses as A and B. A will create one field at that point, and that field created by A will be towards A itself. Gravitational field is always towards the mass that creates it. Let's call this field due to A, EA. And B will also create a field, and that will be towards B itself. Call it EB. We need the vector sum of these fields, and since they are not in the same direction, even if you know their magnitudes, you can't add them directly. Okay, let's see what can be done. The gravitational field created by A would be Gm divided by the distance squared becomes d square plus x naught square. And B will also create the same amount of gravitational field because it is the same mass, same distance. So the strengths of gravitational fields they produce are equal, but they are not in the same direction. So we have to use the resultant. We may have to use the resultant formula. To use the resultant formula, okay, root of a square plus b square plus 2ab cos theta, resultant of two vectors, we need to know what is the complete angle between the vectors. This is not known. Using some geometry, we can find out. But instead of that, there is a simpler method, slightly easier method. What we can do is, we can resolve each of these fields into x and y components. Okay. EA, its y component will be upwards and x component will be to the left. Okay, to get the component also, you need to know some angle. We'll come to that. So these yellow components are the components of EA. Similarly, EB will have a y component in the downward direction, but an x component towards left itself. And you can see there is a symmetry in this situation. Call this angle as theta, angle made by any one of the fields with the x-axis. Let's take it as theta. I'm not taking the total angle between the vectors. I'm taking the angles with x-axis. They both make the same angles with x-axis and they both have the same magnitude, means they will have equal y components, but they are in opposite directions. So the two y components will cancel out. You don't have to bother about them. Therefore, the net field in this case will simply be the sum of EA's x component and EB's x component. Okay. We know E and EB's magnitudes. to get x component, we need to multiply it with cos theta because they make an angle theta with the x-axis. How to get cos theta? You can see that there are right angle triangles that have formed here. This is a right angle triangle and theta is a part of that triangle. Then it's simple to get cos theta. Adjacent divided by hypotenuse. Adjacent is x naught. Hypotenuse is root of d square plus x naught square. That's all. Now that becomes EA is GM by d square plus x naught square. It's if you want its x component, you will have to multiply it with cos theta. And cos theta is adjacent side x naught divided by hypotenuse root of d square plus x naught square. And EB's x component also will be the same because magnitude of EB is same as magnitude of EA. And EB also makes the same angle theta with the x-axis. So I can just multiply this with 2. Because there are two such fields. That's all. Therefore, the net gravitational field at that position becomes 2gmx0 divided by, denominator can be simplified as d square plus x naught square whole power 3 by 2. Okay. Anyway, this is not a formula that you need to remember, but remember the approach. You were given 2 point masses and asked to find out the net gravitational field at one place. This is how we do it. We first visualize the individual fields. Then we get the net field. Okay. Next, and this result is important. And remember one more thing. Whatever you learn in this chapter, gravitation, the same ideas you will be applying in the first chapter of 12th class, electric charges and fields. Okay. Masses exert gravitational force on each other. Charges exert electrostatic force on each other. And the behavior of gravitational force between masses is very similar to the behavior of electrostatic force between charges. Okay. So these derivations will be useful in 12th class also. Right? And if any of you choose to continue these classes for 12th class also, we will not be discussing those derivations completely again. Okay. Whatever derivation we do here, the result will be used directly in 12th class. Okay. So consider a system like this. We now need to find out the gravitational field due to a uniform ring on its axis. Okay. Consider a ring like this. See, ring is a circular object. We are looking at it from an angle. So it looks like this. Assume its mass is m and its radius is r. What we want to find out is the gravitational field that it produces at a certain distance on its own axis. Axis of the ring is a point passing through its is a line passing through its center perpendicular to the plane of the ring itself. So this is the axis of the ring. So at some point here, let's say the point is at a distance a from the center. At that point, we need to find out how much gravitational field the ring produces. Okay. Can any of you give any idea what can be done? How to derive the net gravitational field produced by a ring at that point? See, what do we know so far about gravitational field? We know the definition. Field is force per unit mass. Now, you can't just assume there is a mass present here. Write an expression for force between them. We don't know the force exerted between force acting between a ring and a particle. Okay, rod and particle we solved in the last class. Maybe that if it had been a rod, we could have done something like that. Between a ring and a particle, we don't even know what force acts or how much force acts. Okay, so that approach will not work. Then the only other approach we are left with is to consider the ring as a collection of particles, because we know how much gravitational field a point mass creates, gm by x square. So we have to treat this ring as a collection of point masses now. Okay. So consider any one element of the ring, maybe this one. It will have some mass. Call the mass as dm. Okay. That's a small part of the total mass of the ring. Okay. That mass dm, it will be at a certain distance from this point. Let's call that distance as x. If you know, okay, you have considered a point mass dm at a distance x. That point mass will create a gravitational field at this position now. In which direction does a mass create a field? Towards itself. So there will be a gravitational field created by it in this direction. Since it's just one element of the ring, it only creates a small gravitational field, dE. That's the field produced by one element. After that, what we need to do is we need to visualize field produced by all elements at that place and add them by treating them as vectors. Okay, so we'll go step by step. We have considered a mass dm here. So what I want you all to do first is write an expression for the field created by that mass. And the distance x is not known to us. You have to answer in terms of radius of the ring and the distance a. And that's not very difficult. You can do it. So one of you can unmute and tell how much is the field created by this element at that position. The formula for field due to a point mass is g multiplied with mass divided by square of the distance from the mass to that point. Here we want the field created by dm. So it will be g mass is dm divided by square of the distance between that particle and this position. Now the distance between particle and position is root of r square plus a square. You square it, it simply becomes r square plus a square. That's the gravitational field produced by one element at that position. This is not the only field that is getting created there. All other elements will create the fields. Consider another element. Let's take an element diametrically opposite. Okay, on the lower side of the ring. Its mass also can be taken as dm. Can one of you tell me how far this element will be from that position? What will this distance be?
Same root.
Same, root of
Root
r
of
square
r.
plus a square. Correct. And this element will be creating a gravitational field at this position towards itself. Okay, every mass creates gravitational field towards itself only. D. Do you think this will be the same amount of field as the other one or not? I think I've
It
shown
should
it
be,
slightly
sir.
longer, but yeah, it should be the same. Why? Because it's the same dm that we are considering and the distance is also same. Therefore, the field strength should be same. Okay. What about other elements? Aishwarya, you tell me, if we consider another element somewhere here, do you think that element also will be at the same distance from that position and create the same amount of field or not?
Yes.
It will be. See, in the diagram, okay, that we draw on the screen, it may feel like this distance is different. Okay, but this is actually a three-dimensional diagram. You have to visualize this like a cone. Okay, the ring here is the base of the cone. And this point here is the apex of the cone. Then you can visualize that all the distances from every element of the ring to the point on its axis are going to be the same. Okay, on screen in 2 dimensions, it looks like these distances are different, but they're actually all same. Okay, so all elements of the ring are going to create the same amount of gravitational field at that position. Fine. But the problem now is that the fields created by all elements are not in the same direction. Each element creates a field towards itself. So basically what will happen is you will see a bunch of vectors here, bunch of field vectors like this. Those vectors form a cone. Okay. Each individual element of the ring creating a field of its own. You'll see a bunch of field vectors like this. They'll be shaped like a cone. Okay, some out of your screen and some behind your screen. Okay, the yellow one is the topmost one. The green one is the bottommost one. In between, there will be others. Okay, all these vectors are of the same strength. Now, you all answer in chat. What do you think will be the direction of the resultant of all these vectors? Just the direction of resultant of all these vectors, I want you to answer. Type your answers in chat, all of you. Since all the vectors are of the same strength, their resultant means their combined effect is going to be towards left, towards the center of the ring. This is the direction of net gravitational field at that point on its axis. From symmetry, we can say. Okay, now we need to derive the expression for that net field. We have the expression for individual fields created by each element, G dm by r square plus a square. Okay. Now net field is going to be towards left. So what we are going to do is we are going to add their x components. Y components will get cancelled anyway. Now how did I say that the y components are going to get cancelled? Let's visualize it once. Just a moment. Now this is one element's gravitational field that we have visualized. Another element's gravitational field, the bottommost element, its gravitational field is this way. Now these two are diametrically opposite elements. The yellow one will have a y component of field like this. The green one will have a y component of field like this. And due to symmetry, these two will be of the same strength, they'll cancel. Their y components will cancel. Likewise, for every element of the ring which is producing a field there will be a diametrically opposite element which cancels the field perpendicular to the axis. Only the field component along the axis will survive. For example, this yellow vector, its x component is to the left. The green one's x component is also to the left itself. So not just these two, all elements of the ring, their fields x component only will be left finally. The y components, z components will get cancelled. Okay. So what we are going to do is same as what we did in the previous question actually. Assume this angle is theta. The entire bunch of cones will make the same angle theta with the x-axis. Okay. Bunch of vectors, not cones. The entire bunch of vectors will have the same angle theta with x-axis. So what we are going to do is we are going to write x component of dE, which is dE cos theta. Okay. What is dE or how much is dE? Gm by r square plus a square. Multiply that with cos theta. Cos theta is adjacent by hypotenuse. Adjacent side is a. Hypotenuse is root of r square plus a square. So a by root of r square plus a square. That is cos theta part. This is the x component of one of the fields. And what we finally need is the summation of x components only because the net field is going to be in the x direction. Okay. So if you first visualize what is the direction of net field, it becomes easy to solve. Therefore, net gravitational field at that position is integral of the x components of the small fields. So it becomes integral of, what do you have to integrate? G a dm divided by r square plus a square whole power 3 by 2. Now in this integral, m is the only variable. There's no other variable. You just have to integrate it with respect to m. Because a is a fixed distance on the axis where you want to find out the field. And r is the radius of the ring. That won't change anyway. G is universal gravitational constant. Therefore, the net field becomes Ga by r square plus x square whole power 3 by 2 multiplied with integral dm, and integral dm simply becomes the total mass of the ring. That's all. Therefore, the net gravitational field produced by a ring on its axis becomes Gma divided by r square plus a square whole power 3 by 2. Where m is the mass of the ring, a is the distance on its axis from the center where you want to find out the field. R is its radius. And what is the direction of this field? Towards the center of the ring. So the ring creates this much influence on its axis. And if some mass enters that position, you can tell how much force the mass will experience due to this ring. So that is what is gravitational field. Field helps you calculate force. And the existing system creates the field. Another mass which comes there experiences the force due to the field. Okay. And it is very important to remember that this result is for a uniform ring. What does a uniform ring mean? Mass is distributed in the same manner everywhere. All the dms will be same. Okay. If it's not a uniform ring, then this bunch of vectors that is there, they won't all have the same strength, same magnitude. Then you can't say that the resultant will be along the axis. Okay. Only when two vectors are of equal magnitude, resultant will be exactly between them. If they are not of equal magnitude, then it depends which one is longer. Depending on that only, you can tell what will be the direction of net force or net field. Okay, hope this is clear to all of you, how we derived the gravitational field on the axis of a ring. And if you observe this result, no, it is very similar to the previous problem's answer. Previous problem also, we got the same answer actually. Okay, like what is the answer we got now? Gma by r square plus a square whole power 3 by 2, because m was the mass of the ring. In the previous problem, we took two masses, m and m. So the effective mass of this system is 2m. And the answer we got is almost the same. G into the effective mass 2m into distance. In this problem, we called it as x naught divided by b square plus x naught square whole power 3 by 2. So two equal masses on their perpendicular bisector or a ring on its axis create the same amount of field. Only thing you need to be careful is two equal masses means you have to add both masses. Ring means you just take the ring's mass. Okay. So we discussed gravitational field produced by point mass, combination of point masses, ring on its axis. Let us make use of all this now. Direct application. Let's say there is a ring of mass m, radius r. On its axis, at a distance, let's say r root 8. Okay, at that distance on its axis, there's a particle present. And how much mass shall we assign to the particle? Let's say 3m. Okay. So ring has mass, particle has mass, mass will attract. Find out the force of attraction between them. Calculate gravitational force between the ring and the particle. Do this quickly. The previous case, we struggled so much to find out how much field a ring creates, no? And if you know how much field is present at a particular place, you can tell how much force a particle there experiences. So this ring will create a gravitational field here first. Not first, we can't say first this will happen, then that will happen. The ring will create a gravitational field there. Find out how much that is. And the point mass 3m is in the presence of that field. If mass is in the presence of a field, you can tell how much force it experiences. That's the idea. Now we just derived the formula for gravitational field of a ring on its axis. Gm a divided by r square plus a square whole power 3 by 2. Here the distance a is given as r root 3, r root 8. Simple. Divided by r square plus r root 8 whole square becomes 8r square whole power 3 by 2. This effectively becomes Gm r root 8 divided by denominator r square plus 8r square 9r square whole power 3 by 2. 9r square under root is 3r whole cube becomes 27r cube. One r can be cancelled and you will be left with root 8 Gm by 27 r square. That's the gravitational field created by the ring at that position. And 3m is in the presence of that field. 3m is a point mass. Okay. Therefore, the force acting on 3m, how do you calculate force from field? Field multiplied with the mass. That's all. Field is root 8 Gm divided by 27 r square multiplied with the mass 3m. 9 times, that's the answer. Root 8 divided by 9 Gm square by r square. That's the force exerted by the ring on the particle. Then as a reaction, the particle on the ring also will exert the same amount of force. So we say this is the force of attraction between them. Rishi, where were you stuck? Why could you not answer this problem?
Your calculation error because of the 3 by 2.
Okay, power 3 by 2. Fine. Power 3 by 2, you can take power 3 and then power 1 by 2. Or you can take power 1 by 2 and then power 3. Okay, that's what I did. Fine. Next, let us discuss the graph of the gravitational field produced by a ring on its axis. Consider a ring, uniform ring, okay, need not mention again and again. Assume its mass is m, radius is r. At different points on its axis, it will create fields of different strengths. Okay. Let us take a random point which is at a distance x. So in place of a, I am taking x. If the distance is x, the field there becomes Gm x divided by r square plus x square whole power 3 by 2. That's the formula for field strength at a certain distance. We have to draw the graph based on this equation, based on this formula. Okay. For the center, the distance is 0. And as you move away from the center, distance increases. So on x-axis, you have the distance on the axis of the ring. And on y-axis, you are showing the field strength, magnitude of the gravitational field. Okay. One of you tell me, when x is 0, how much is the gravitational field? Based on the formula you tell. When x is 0, how much does the gravitational field become?
0, sir.
0 itself. That means at the center of the ring, the net gravitational field produced by it is 0. And it makes complete sense. You can visualize it like this. Assume this is the ring, okay, seen from the front. This is the center. Every element of the ring creates a field at the center towards itself. But for every element, there will be a diametrically opposite element creating an equal amount of field in the exact opposite direction. And those fields will all cancel out. And that is how the net field at the center exactly becomes 0. One field this way, one field this way, they'll cancel. They're all of the same strength. No, they're all at the same distance from the center. So all fields will cancel. Net field at the center becomes 0. Okay. So the field at the center of the ring is 0. So the graph starts from the origin. When distance is 0, field is 0. But when x becomes non-zero, the field also becomes non-zero. Okay. Let's study this formula a little first. gmx by r square plus x square. First case, we are taking x is equal to 0. And if x is 0, the field becomes 0. Okay. Next case, let us take a large distance from the ring. Means x is much greater than r. Not infinity, but a large distance. Means more than 10 times of the radius or something like that. Can one of you tell me what adjustment can be made in this equation if x is very large compared to the radius r? How can we change this equation? Or what can we change this equation to? One of you unmuted. What did you say?
The gmx by x square into x square power
Okay,
3 by 2.
so you are saying we'll ignore r square. That is correct. See, when two numbers are being added, and if one of them is extremely large compared to the other, you can ignore the smaller one and approximate it to the larger one itself. Approximate the sum to the larger one itself. It's a mathematically valid procedure. So if x is very large compared to r, then obviously x square will be much larger compared to r square. So if x square is very large compared to r square, we'll ignore r square altogether. Then the formula for the field becomes gmx by x square whole power 3 by 2. X square whole power 3 by 2, this square and power 2 will cancel. Denominator becomes x cube. Effectively, the formula changes to gm by x square. And this is interesting. Gm by x square is the formula for field produced by a point mass, right? We derived that today itself. So what does this show us? It shows that when you go too far from the ring behaves like a point mass. And makes sense. When you go too far from the ring size won't matter. Okay, the actual mass distribution won't matter. You can treat it as a point mass. Okay, good. Next case. Suppose x tends to infinity. You go to infinite distance from the ring. If x tends to infinity, then the gravitational field becomes 0. Okay, because x square tending to infinity, denominator tending to infinity means the whole thing becomes 0. Okay, now observe what is happening here. At the center of the ring, the field is 0. At other distances, the field is non-zero. Again, at infinity, it becomes 0. So how do you think the graph will look? It should start from 0, become non-zero, again tend to become 0. Means it has to increase and decrease again. Okay, as x tends to infinity, the field will be tending to 0. Then, needless to say, you can understand that there is one point or there is one distance where the field is the strongest. Field produced by the ring is the strongest. Okay. We'll discuss that. I'll give you some steps in the worksheet. Okay, yesterday I could not send the worksheet because of some urgent work. But tomorrow I'll send you a worksheet in which there will be a proper derivation for this and you all have to do it and send. It is compulsory to solve worksheets. Okay, because some cases I'll have to give in the worksheets which cannot be discussed in class. And you are supposed to apply what you learn in class. No, that is why I'm giving you worksheets. There's no point in me teaching you everything. I'll teach you the important concepts that are required. You should apply them to some new situations. If you make mistakes, I will correct. Okay, that is the purpose behind giving those worksheets. You have to solve. So this is how the field produced by a ring on its axis varies. It increases and then decreases. So there will be one distance from the ring, from the center of the ring, where the field it produces is the strongest. Okay. Fine. So that is all for today. Let's quickly go through what all we discussed. So we first talked about what is a gravitational field. Any mass in this universe influences the space surrounding it. Up to how much distance? Up to any distance. There will be an influence. That influence is what we call as its gravitational field. And the strength of that influence is the magnitude of gravitational field. It's also called gravitational field intensity. Okay. So by definition, gravitational field at a particular position is the force experienced per unit mass present at that position. So if you want to find out the field somewhere, imagine a point mass present there. If it's already there, okay. If it's not there also, imagine it is there. calculate the force that it experiences. Force divided by the mass will give you the field. We solved some problems based on this. We used it in reverse also. If you know field, you can tell the force that a mass experiences. Point object, extended object. Then who creates fields? Masses create fields. So we found out how much field a point mass creates at a certain distance from it, gm by x square. The formula is very important. We'll be using it frequently. And this field will be directed towards the point mass that is creating the field. Okay, gravitational field is always attractive in nature. Then the graph of that, some questions based on that. Then the gravitational field of a ring on its axis and its graph, problem and graph. Okay. Next class, we will discuss the gravitational field produced by spheres, hollow sphere and a solid sphere, inside, outside. Now, in case of hollow sphere, solid sphere, we are not going to derive. We'll directly use the results. Derivation of field produced by hollow sphere, solid sphere, you will learn in electrostatics 12th class. Ring field we derived here, we'll use it directly there. Spheres fields we'll use directly in this chapter, but derivation will be done in 12th class. Okay, but anyway, there you won't face any difficulty. It's easy only. Then once we discuss fields produced by spheres, we can talk about gravitational potential energy, energy conservation based problems, then gravity of a planet, how a satellite revolves around a planet, all those things. Okay, thank you all. We'll continue in the next class.
Thank you.
Thank you, sir.